A seismic shift is occurring in the processor industry, one that threatens to upend decades of established dominance. RISC-V, an open-source instruction set architecture, has emerged as a formidable contender in a market long controlled by proprietary giants. The question is no longer whether RISC-V will gain traction, but rather how profoundly it will reshape the competitive landscape. RISC-V represents a fundamentally different approach to processor design. Unlike the proprietary architectures that have dominated computing for decades, RISC-V is an open standard maintained by a nonprofit foundation. Any organization or individual can implement RISC-V processors without paying licensing fees or seeking permission from a controlling entity. This openness stands in stark contrast to the closed ecosystems of x86 and ARM, where intellectual property restrictions and licensing agreements govern every implementation. The architecture itself adheres to reduced instruction set computing principles, emphasizing simplicity and efficiency. RISC-V specifications define a base integer instruction set along with optional extensions for various capabilities. This modular design allows implementers to tailor processors precisely to their requirements, including only the features necessary for specific applications, while omitting superfluous functionality. Intel and AMD have maintained their stranglehold on the personal computer and server markets through decades of iterative improvements to the x86 architecture. Their processors power the overwhelming majority of desktop computers, laptops, and data center servers worldwide. This dominance stems from extensive software ecosystems, backward compatibility guarantees, and substantial investments in manufacturing technology. The x86 instruction set, despite its complexity and historical baggage, remains the de facto standard for general-purpose computing. However, this entrenched position faces unprecedented challenges. The open nature of RISC-V eliminates barriers that have historically protected incumbent architectures. Companies no longer need to negotiate licensing terms or pay royalties to design custom processors. This democratization of processor development has profound implications for innovation and market dynamics. Customization capabilities represent one of RISC-V's most compelling advantages. Organizations can design processors optimized for specific workloads without the constraints imposed by general-purpose architectures. A company developing artificial intelligence accelerators can include only the instructions relevant to machine learning operations. An embedded systems manufacturer can create minimal processors that consume minimal power and occupy minimal silicon area. This flexibility proves particularly valuable in specialized applications where off-the-shelf solutions impose unnecessary overhead. Cost considerations further enhance RISC-V's appeal. The absence of licensing fees reduces the financial burden of processor development, particularly for high-volume applications. While designing a competitive processor still requires substantial engineering expertise and resources, eliminating royalty payments can significantly improve profit margins. For price-sensitive markets, this economic advantage becomes increasingly important. The architecture's simplicity also facilitates verification and security analysis. RISC-V processors can be thoroughly examined and validated because the instruction set specifications are publicly available. This transparency enables independent security audits and reduces the risk of hidden vulnerabilities. In an era of increasing concern about hardware security and supply chain integrity, the ability to scrutinize processor designs carries considerable weight. Real-world adoption of RISC-V has accelerated dramatically in recent years. Major technology companies have announced RISC-V initiatives spanning diverse application domains. Western Digital has committed to transitioning billions of processor cores to RISC-V architecture across its storage products. NVIDIA employs RISC-V processors as microcontrollers within its graphics processing units. Alibaba has developed high-performance RISC-V cores for cloud computing applications. These implementations demonstrate that RISC-V has progressed beyond academic curiosity to become a viable option for production systems. The embedded systems market has proven particularly receptive to RISC-V adoption. Microcontrollers based on RISC-V architecture have proliferated in Internet of Things devices, industrial automation systems, and consumer electronics. The ability to customize processors for specific embedded applications while avoiding licensing costs makes RISC-V an attractive alternative to established architectures in this segment. Despite these successes, RISC-V faces formidable obstacles in challenging Intel and AMD's core markets. The software ecosystem surrounding x86 architecture represents decades of accumulated investment. Operating systems, compilers, development tools, and applications have been meticulously optimized for x86 processors. Replicating this ecosystem for RISC-V requires sustained effort from numerous stakeholders across the industry. Performance parity presents another significant challenge. Intel and AMD have invested billions of dollars in microarchitectural innovations that extract maximum performance from the x86 instruction set. Their processors incorporate sophisticated features such as out-of-order execution, speculative execution, and extensive caching hierarchies. While RISC-V's instruction set architecture offers theoretical advantages, translating these into competitive real-world performance demands substantial engineering expertise and manufacturing capabilities. Manufacturing technology constitutes yet another barrier. Intel and AMD leverage cutting-edge semiconductor fabrication processes to produce processors with billions of transistors operating at high frequencies. Achieving comparable manufacturing sophistication requires access to advanced foundries and substantial capital investment. While RISC-V's open nature facilitates design innovation, it does not inherently solve the challenges of semiconductor manufacturing. The server and data center markets present particularly difficult targets for RISC-V disruption. These environments demand not only raw performance but also extensive software compatibility, robust ecosystem support, and proven reliability. Enterprises invest heavily in infrastructure built around x86 processors and exhibit considerable inertia when considering architectural transitions. Convincing data center operators to adopt RISC-V systems requires demonstrating clear advantages that justify migration costs and risks. Nevertheless, RISC-V's trajectory suggests a future of increased architectural diversity rather than outright replacement of existing platforms. The architecture excels in domains where customization, cost efficiency, and transparency outweigh the benefits of established ecosystems. Specialized accelerators, embedded systems, and emerging application areas may increasingly favor RISC-V implementations. Meanwhile, x86 processors will likely retain their dominance in markets where software compatibility and ecosystem maturity remain paramount. The geopolitical dimension adds another layer of complexity to this competitive landscape. RISC-V's open nature and international governance structure make it attractive to nations seeking technological sovereignty. Countries concerned about dependence on American or European processor technologies view RISC-V as a pathway to indigenous semiconductor capabilities. This geopolitical motivation could accelerate RISC-V adoption independent of purely technical or economic considerations. The processor industry appears poised for a period of coexistence among multiple architectures, each optimized for different use cases and market segments. RISC-V will likely capture significant market share in specialized applications and emerging domains, while x86 maintains its position in traditional computing markets. This architectural pluralism may ultimately benefit the industry by fostering innovation and preventing monopolistic stagnation. The rise of RISC-V represents a fundamental challenge to the established order of processor design, but not necessarily an existential threat to Intel and AMD. The open architecture has demonstrated genuine technical merit and achieved meaningful commercial adoption. However, displacing entrenched incumbents in their core markets requires overcoming substantial technical, economic, and ecosystem barriers. The most probable outcome involves RISC-V establishing itself as a significant player in the processor landscape, while x86 architecture continues serving markets where its strengths remain most relevant. The future of computing may be characterized not by the death of traditional architectures, but by their coexistence with the innovative alternatives in an increasingly diverse technological ecosystem.